Before we start the next lesson, I just want to review a couple concepts that we have gone over in our past. One of them has been focused on solving quadratic equations. For instance, if you had a quadratic equation that took on this view, it's an equation because it's equal to 0. It's quadratic because it is a second degree polynomial. It's on the left-hand side of the equal sign. One of the ways that we learned how to do this was by factoring it and finding two numbers that can add to give you 5 and multiply to give you 6, both positive. Those two numbers would be 2 and 3. 2 plus 3 is 5. 2 times 3 is 6. So in my factors, I would write x plus 2, x plus 3. Using the 0 property, we would know that in order for me to multiply two things and get 0, one of the factors has to be 0. So if I wanted to ask what I plug into x to make this factor 0, I would combine a positive 2 with a negative 2. The second one, likewise, would be a negative 3, and this would be considered solved. Remember that when you have a quadratic equation and you have it graphed, and always when you have a quadratic equation, it either takes on the picture of a smile or a frown. We also can find the solutions by looking for the zeros. In this case, if we were to graph this, it would look something along the lines of my sketch. It would have one of these zeros be at where x is negative 3, and one of these zeros be where x is negative 2. And so there's been a few different ways that we've learned how to solve quadratic equations. One of the things that we haven't talked a whole lot about is what happens if you have a quadratic equation that does not have a perfect set of numbers that will give you what you are trying to find. For instance, I have 6 and negative 5. So if I were to add two numbers to get 6, but multiply them to get negative 5, really I only have one option, and that is 1 and 5. In order for this to be true, it has to either be a negative 1 or a negative 5. But if you were to combine both of these by addition, you would not get 6. And so this would be one of those cases where this could not be factored using the AC method or using the box method or anything like that. But that doesn't mean that this doesn't have solutions. So we need another strategy for trying to find the solutions to a quadratic equation when we're not able to factor it. Another concept that I want to go over real quick and make sure that you recall is when you are simplifying radicals. Remember that anytime you're simplifying a radical, you are looking for squared numbers the best that you can if you're doing a square root. For instance, if you had the square root of 25, and I simplified it, it would be 5. But remember, if you have a negative symbol under the radical, people would say that this is going to give you a not real result, which means that you're going to have to go into another realm of numbers in order to be able to simplify this further. We have done this thing where we have split this up so that it is the product of two radicals, so that I can pull out the negative symbol. If you remember in the past, if you can pull out a negative 1 under the radical symbol, then you can change that to I, which stands for imaginary number. And we could simplify this by saying that the square root of 25 is 5, and the square root of negative 1 is I. Let's just try another one real quick. So if you have negative 200, and the first thing you would do is kind of try to pull out the perfect square number. In this case, a perfect square would be like the square root of 100. And in order to get 200, I have to multiply that by the square root of 2. And then also we have to have the square root of negative 1. So I have broken this down so I have a square number, I've pulled out my -1, and I've found the third factor that would make this equal to what we started off with. The square root of 100 is 10. I still have radical 2, and I can convert this radical -1 to I. That being said, that takes us into the notes for the third home lesson. And basically, the concept here is that we're trying to find the solutions to quadratic equations using what we call the quadratic formula. The quadratic formula can be used when you have a quadratic equation that's in general form that takes on this ax squared plus bx plus c. Remember that the a, b, and the c represent the numbers that are in front of the first and second term. C is the constant that's at the very end. Also know that the very first term cannot be 0, because if it was, that would cancel out my x squared and we wouldn't have a quadratic anymore. We would have a linear. So this quadratic formula only works for quadratics. The quadratic formula is actually kind of a true plug and chug situation where you are plugging numbers in for a, b, and c, and those numbers are derived from the quadratic formula or the quadratic equation that you're starting off with. Even furthermore, if you look deeply into the quadratic formula, you will find this, this portion that's under the radical symbol, which we call the discriminant. And the discriminant, if you were to go ahead and plug some numbers into here, can give you clues as to what type of roots you're going to find or not find. For instance, if I plug all my numbers in here and I end up getting a number that is greater than 0, that would tell me that we have two roots. They are real numbers, and they are not equal. So sometimes you can get two roots that have the same numbers at the end, and if that happens, that's great. But if this happens, then it means that you have two roots, they're not equal, and they're real numbers. If you were to go ahead and simplify the discriminant after plugging in numbers, and it's exactly equal to 0, that means that you have one real root, and it's equal. So it would be like x plus 2 and x plus 2, or x minus 1, something like that, which would result in one answer. And then if you were to plug numbers into the discriminant and then end up with some kind of number that is less than 0, it would mean that there are complex roots. And remember, complex roots means that you'll see I in there somewhere compensating for a negative symbol that's under the radical. So that's just a thing. It's kind of interesting. And just so you can see this visually in a graph, if the discriminant was a negative number, that was the third option here, and it was graphed, it would look something like this. It wouldn't be touching the x-axis. If the discriminant is 0, that was our second example, that would look like our green graph, where the vertex of my parabola just touches 0 once, just touches the x-axis once. And then if your discriminant is positive, that was our first example, you can see we have that traditional quadratic equation, or quadratic, yeah, that touches the x-axis more than once. And it's not necessarily centered right in the center, but these are also clues as to what you would get if you were to use the quadratic formula. Here's some examples of quadratic equations that we want to use the quadratic formula for. Before we do anything with our quadratic equations, we have to make sure that they're in general form, which means that my x squared term is the first term, the x term is the second constant, and then it's equal to 0. So I would have to transform number 1 by subtracting 2x from both sides and subtracting 48 from both sides, and make this x squared minus 2x minus 48 is equal to 0. I need to find what x could be to make this a true statement. So I'm going to go ahead and I am going to put a set of parentheses inside my quadratic formula anywhere where I'm going to plug something in. To make things even easier, I'm going to identify what is going to be my A, my B, and my C. If I were to look at this, A would be 1, because there's a 1 in front of the x squared. B would be -2 because there's -2 in front of the x, and C would be -48 because C is the constant, and that is -48. Anywhere in my formula that I see A, I'm going to plug in a 1. That is right here and right here. Anywhere in my formula that I see a B, I'm plugging in -2. So that happens here and here. And then anywhere in my formula that there's a C, I'm going to plug in a -48. A lot of people have different ways that they choose to have this simplified. I usually will simplify the discriminant first before anything, and I know I'm using a ton of room, so I want to make sure I'm also making this easy to understand. -2 is +2. If I were to simplify the discriminant, -2 squared is 4. 4 times 1 times 48 is 192. Remember that we have a -4 times a +1, which is -4. -4 times -48, that's going to give me a positive. So this actually gives me as a discriminant the square root of 196. So I'm going to put that right here. And then this is over 2. To determine whether or not 196 is a square number, I'm going to go ahead and put it in Desmos. So after putting it in Desmos, I can see that the square root of 196 is 14. So now I'm going to rewrite this as 2 plus or minus 14 over 2. This is representing two different answers because I have to figure out what the positive version is and what the negative version is. If I go positive, 2 plus 14 is 16 over 2. If I go negative, 2 minus 14 is -12 over 2. That will give me the two solutions. One of them is 8 and one is -6. This shouldn't be a surprise because remember, in the past when we looked at the first page of this, it said if the discriminant was a positive, then that would mean that you have two real roots that are not equal to each other. So really interesting. Go ahead and take a moment. I want you to do number 2. I'm going to erase some of this stuff and get it out of the way, and then we'll go over it together. So pause the video right now and then do number 2. Okay, so I erased out what we had there for number 1 so that we would have some space. Left my solutions there. For number 2, if I go ahead and write this in general form, I still have my 2x squared. I have to move the -18x to the overside by adding it. Plus 39 equals 0. I'm going to identify what A, B, and C is. A in this case is 2. B in this case is going to be 18. And then C is going to be 39. If I write my quadratic formula, I have -b plus or minus the square root of b squared minus 4 times a times c all over 2a. And I'm going to go ahead anywhere where I see a that is supposed to be plugged in, I will put a 2. Anywhere I see there's supposed to be a b plugged in, I will put 18. And anywhere I see that C is supposed to be plugged in, I will put 39. Now, I'm going to go ahead and start writing things out. For instance, my -18 stays the way it is. If I was going to go ahead and do the discriminant, this time I'm going to put this in Desmos. So after putting this into Desmos, I have a discriminant of 12. It's a positive number, so that makes me expect 2 real roots that are not equal. And this whole thing is going to go over 4. If I were to simplify radical 12, I could do that because I could pull out a 4, and 4 is a perfect square. 4 times 3 is 12. I can simplify square root of 12 and make it 2 radical 3. And it's not unusual for you to actually leave your answer in this form. Recognize that this represents 2 answers because we have that plyness symbol there, but it's okay if you leave it in this form. So this is okay. You don't have to take it further than that if you don't want to. I want you to now pause and do number 3, and then come back to the video and we'll do this one together. Okay, so looking at number 3, my A is going to be 5, my B is going to be 3, my C is going to be 1. Let's go back here. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And wherever I see a, I'm going to put a 5. Wherever I see a b, I'm going to put a 3. Wherever I see c, I'm going to put a 1. And then I'll start to simplify. Negative 3 plus or minus the square root. We have 3 squared is 9 minus 20. It's going to give me negative 11. If you recall, if there is a negative number, a number less than 0 under the discriminant, then that means that you have non-real roots. You'll have complex roots. That's okay. We're just going to have to make sure that we express that with I and not leave the negative under the radical symbol. So what I'm going to do is I'm actually going to break this up so that I pull out my negative 1. And then I'm going to rewrite it, expressing that square root of negative 1 as I, and leaving the rest of it be. So again, you can leave this. This represents 2 separate answers, but that is okay for you to leave it just like that. Our final example, I had to bring it back, so I erased it. I want you to go ahead and take a moment and do number 4. You're going to pause the video and then come back and we will do this one together. So if I go ahead and plug this in, I will have negative 50 plus or minus the square root of 50 squared minus 4 times 5 times 125 all over 2 times 5. This is complicated enough for me to want to put this in Desmos to figure out what my discriminant is, so I'm going to do that. So go ahead and look up here. This is the result 0. So if you recall, if the discriminant is 0, that means that there is going to be one real solution. And if this was going to be graphed, it would just touch the x-axis once. So negative 50 over 10 is going to simplify to negative 5, and that's the one solution.